So this class is very important in the sense that we'll finish off with the SVD numericals, and also we'll touch upon the portions which are important for your examination purpose for your CAT 2. And related to that, if any other specific numericals or more extra numericals which we can fit in within the time duration, we'll do that. But prior to going there, let us complete this portion on singular value decomposition for a MIMO channel. So if you remember on last day's class, we had already discussed that this primarily is a tool in making sure the complex channel matrix can be decomposed into simpler matrix, and each of the matrix which usually looks something of this nature, U, sigma and V. This particular U, V and the sigma arrays of the matrix individually provide some information regarding the channel, which in general, if you try to solve directly from H, may be very difficult to attain. So that is why we usually do some matrix manipulations, and basically we try to find out simpler terms on U, and because U and V are both unitary matrix, as well as the sigma is a diagonal matrix. So accordingly, we have also observed that there are certain properties that all this matrix will be following. Hopefully you have noted down this in last day's class itself, because this happens to be the main idea behind this decomposition. All the rules which you are looking at, the six logical rules that you are looking at, many of them, as I told already, they come in directly from the property of the matrix itself, especially the U and the V's. They are supposed to be coming in directly from the property of matrix. But apart from that, the sigma also you can see over here, it also bears the resemblance of a diagonal matrix with sigma 1, sigma 2 up to sigma t, and keeping in mind that the order of the sigmas will always be sigma 1 greater than sigma 2 and so on and so forth. Alright. So the basic objective of these questions are to find this three decomposed matrix and test whether they are following the property. That is all we have for our syllabus. Alright, so we don't need to go into the further detail of what we can interpret from the results. Although, as I said, here is in some of the information over here, that what are the important segments that we can say from U and V. Although this is theoretical aspect that I told you, but practically how it happens, it is beyond the scope of this class. And as I said, there are many other algorithms, non-linear algorithms also, which works with respect to these algorithms with this SVD, which is again not there with for us to understand right now, and it is sufficient to just prove that whether the decomposed outcome is following the rules or not. That's all. Okay. So based on that, I had started off with a very simple example where we have H, which is having a 1 cross 1, not a 1 cross 1, actually there are R2 and 2 1. So this is basically a 2, it is a 2 cross 1 matrix. And this also I told you in last day's class, that please remember that the row and the column will be determined by the number of receiver and number of transmitter, and not the other way around. It won't be transmitter to receiver. It should always be read as receiver and transmitter, because H is a matrix which is R cross T dimension and not T cross R dimension. That's how the convention is. So we'll follow in that way. Alright, so keeping in mind the main objective of today's class ideally is, let's see, for this particular example, 1 1 is there, right? Now please understand this carefully, and I'll tell you the other way around what we are supposed to do, and like a double check on this particular question also. You can understand that from the very onset of H, please understand this carefully, the UVW that we have written over there, or the U sigma V that we have written over there, the way it has been decomposed, there is no steps in between. Can you see that? I've directly written out this one. Now, the point over here is two. One is that for a given matrix, which mostly we will follow, you will see the examples also. I'll show you another example. They are of the nature that we can, by intuition, we can decompose them into three matrices. By intuition. Or you can say by trial and error method. Remember the point that we need to make sure that there are three matrices A, B, C, which should multiply amongst themselves in order to get the final result which is given over here. That is basically the intuitive way or the trial and error method, I would tell you. Why I'm telling you this? Because the other way around, the exact method to find out this U, V and the sigma, that involves the eigenvalue calculation, which I'll show you now itself. Alright. But if you are given a question of this nature, and even the next one which I'll show you, intuitively, if you get a hold of how or what should be U, what can be V, what can be sigma, you please go ahead with the intuitive approach only. I'll repeat once again. H to decompose to 3 different matrix can be an intuitive process. Here, as you can see, it is an intuitive way I have done it. Okay? But this is not the correct way, because the point is, when this matrix will be a little bit complex, even if there is some 2 cross 2 most probably, and suppose there are elements present in those matrix, first of all, it is not a one solution that you will get. There can be multiple ways in which you can get the final outcome. That is one thing. So the answers will be different. Secondly, intuitively to find 3 matrix which gets you multiplied and all by a trial and error method might be a little time consuming. But whatever you do, make sure that all this U, V and the sigma follows the properties the 6 properties that I told you. Am I okay with it? So this is how this particular question or some of the questions can be solved. So suppose you are given a matrix, intuitively you decompose it into 3 matrix. Make sure that those 3 matrix multiply and give you the final result. But A, B, C or U, V and sigma should be chosen in such a manner that it follows the 6 properties that I have maintained. Okay, that is the intuitive way. But naturally, that is not the correct way. So I'll show you the correct way also. So in exam, what I want, it's my choice, but I want you to do that correct way only, because that is the way to do it. But if time doesn't permit you, then maybe you can choose out this intuitive way and solve it. Okay, but intuitive process might lead you to some errors, which is a 50-50 chance whether you get it correctly or not. But anyway, we'll just show you that what exactly are supposed to be, because all of the questions leading to SVD involves around that whether you have decomposed this into UVW or UV sigma, and whether UV and sigma follows all the 6 properties as per their matrix. Right. So keeping that in mind, let me just go through this very quickly so that I can show you the exact way of doing this kind of question. So UVW, you can U sigma and V Hermitian we have given. Another thing over here, as I've been telling you for pretty long time now, that most of the time we are going to take the matrix as a real number. So this Hermitian, V Hermitian that you are looking at, it can be, most of the time we will take as V transpose for our convenience. Alright, this I told you in last day's class also, that most of the time for the zero forcing receiver as well as for the MMSC, I told you that we are going to look into mostly as a real valued signal. As we are considering a real valued matrix, we are going to take it as V transpose. We are not going to bother with Hermitian actually. But as in general, the matrix is usually like this. Alright, so that's another thing. Now, as you can see here, after the decomposition has happened, we are trying to prove the properties. Alright, one by one. So as you can see, the first one is U. So the property number 4. So the 4 was, if I go back a little bit, so fourth one is something like U Hermitian U, it should be an identity matrix. So just take the matrix of U Hermitian will be converted to U transpose. So in that way I have given it over here. So that's why, so U Hermitian U, and we are trying to solve them and finding out that this is a value that we are getting as U Hermitian as 1. And basically you will find out that it is the validating the property of it of the same nature. Similarly, you can see that for V also we have done the same thing. So this can also be done. So one line, it's just one line of a proof, because in most of the cases, the matrix that you will come across, they will have ones and zeros, unlike in this case. So many cases the calculation will be easier, and many cases, as I said, it can be done using the calculator, so you don't need to do it manually for that matter. But make sure that you perform the task so that all the properties are maintained. All the properties are valid. For example, here as you can see the sigma part. So sigma we have defined as square root 2. So as you can see here, I have mentioned that sigma is equal to square root 2, which means sigma t is greater than 0. So as per the property 6, there are no other elements actually. So no other element, so only one element is present, and that too is square root 2. So we will consider that, yes, it is validating the property. Alright. So you can see all the properties after you maintain, and rank also if you can calculate. Finally, your answer should be all the properties are maintained for this particular decomposition. Hence, H can be decomposed into U, sigma and V transpose or V Hermitian in the following order. That's all. Right? Right. So in that way, let us take a real example of this SVD and let's see how is the detailed process of finding it. It's a very simple process. It can be adopted for any method, any matrix given to you. So let us solve that first. Because the intuitive solution, I don't think it will be doing any favors to you. But anyway, because of the time, lack of time, you might opt for it. So let me take a real example on how to solve it. Yeah. Let me show you this. Alright, please make a note of this. So the question will be very similar. Find the SVD of the matrix given. So let me just write the matrix first. H is given by 2, 2, minus 1 and 1. Please follow this very carefully. Each and every step, it's very simple actually. A little bit elaborated, that's all. But once you do one question, I think it will be enough for you to solve for the others. Because it's a repetitive steps and the steps you are anyway carrying with you. So you can do it. This will be a confirmed outcome for you. Alright. So now we have 2 cross 2. Now the thing is, what we need is, we know that H is, I'll just opt out some steps for the time being so that we can save a little bit of time. So the equation that we want to achieve is something like this. As you can see, I have mentioned V transpose just because the arrays are in real order. Now, let us try to find out one by one. So the first step, please make a note of this because this is where it is important. The first step is to find H transpose H. So I'll write it down, step 1. Okay, let us try to find out H transpose H. So this means 2 minus 1, we are doing the transpose, and 2, 1 multiplied by H, which is 2, 2 minus 1, 1. And if you do the calculation correctly, you are supposed to get 5, 3, 3, 5 as the outcome, which I am marking as our matrix S. Please stop me if anywhere you are feeling that you are not able to understand. Simple things we are doing. H transpose H we are doing, and we are getting a matrix S. Now why we are doing this? From here we need to find out, I'll just write it down the steps also. Step 2, find the eigenvalues. This you might have done in your numerical analysis and many other subjects as well. Here also we are doing the same. So ideally what we are going to do, S minus lambda I, this should be equal to 0, where I is the identity matrix, lambda is ideally the eigenvalues, and S is the matrix that we have just now found out. Alright. So this is basically what we are trying to find out from the same. So let us try to do that. So my S is 5, 3, 3, 5 and minus of lambda 0, 0, lambda, because it is an 2 cross 2 matrix. So your lambda will also look something like this and it comes to 0. And if you solve them correctly, you are supposed to get a matrix 5 minus lambda, 3, 3 and 5 minus, 5 minus lambda once again. And if you solve them again even more, I'll just mark this as 1. Maybe we'll use it sometime later. We will get an equation lambda square minus 10 lambda plus 16 equals to 0, which gives you two values of lambda, which is lambda 1 equals to 8 and lambda 2 equals to 2. Okay, so we are just trying to solve the eigenvectors and eigenvalues for that matter. Then we'll go for eigenvectors as well. And we are getting the values lambda 1 equals to 8 and lambda 2 equals to 2. Now you might say that why not lambda 1 equals to 2 and lambda 2 is equal to 8? Alright, because it's a 2 roots, so we can apply for any one of them. For that to understand, let me just show you the next step. So Please keep in mind that we have got this. Okay. So the singular values. What are the singular values? Singular values are nothing but the elements of the sigma array. So our sigma array looks something like sigma 0, 0, sigma 2. Why? Can anyone tell me why it is like this? Because if you go back to the material, if I show you the material once again, your sigma looks something like this. Alright, my sigma looks something like this. So you have sigma 1 and sigma 2 as the two diagonal elements. So we want to consider that as well. So we will consider this, and keeping in mind that my sigma 1 should be greater than sigma 2 as per the rule. This is what I was talking about. You can design your matrix but keeping the principles intact. So sigma 1 should be greater than sigma 2, and the sigma 1 is nothing but square root of delta 1, which means square root of 8. And your sigma 2 is nothing but square root of delta 2, or square root of. So your sigma 1 and sigma 2 is this. So hence we can definitely conclude that, see, we have got a confirmed outcome of sigma, or the capital sigma, as square root 8, 0, 0, square root 2. So we don't need any intuition. It is the calculated value. From the eigenvalue itself, we can find out one of the array directly. Okay, no intuition, nothing is required. Just directly you can find it out. Now, if you do it intuitively, you can come across many other results, but you don't know whether they are correct or not. Very common mistake that you will do, I'll tell you right now itself, what you will do is, you will swipe the square root and square root 2 and square root 8. Because that will also give you the same result. But as per the logic, as per the rule, sigma 1 should be greater than sigma 2, hence that is incorrect. Okay, so it doesn't matter whether intuitively you are getting a result. It's important that whether the property is maintained or not. Alright. So this is the first part of it. So that is done for the time being. Now let's take the next part where we're trying to find out the eigenvectors. So let's see the step 3, eigenvectors calculation. Alright. So we substitute first of all the delta 1 of square root 8. So let me write it down. So first, for this value, what we are going to write, we are going to find out, this is a generic method for any system for that matter. What we are going to do is, we are going to substitute in the equation 5 minus delta 3, 3, 5 minus delta. This was already there in the previous calculation when we did the calculation over here. The same equation, equation number 1 we are referring to. So we come back. So this multiplied by a factor a11 and a12. Please do this. This is the general equation when you are trying to find out the eigenvectors or for the particular eigenvalues. Okay, so here as it is a 2 cross 2 matrix, so we will have two set of eigenvectors. So a11 and a12 are this. So this will be equal to 0. Okay, so we have to find out a11, a12 two times. That is once for delta sigma 1 equals to 8 and the other one is for sigma 2 equal to 2. So let's solve it. So let's substitute sigma 1. So 5 minus 8, 3, 3, 5 minus 8 multiplied by a11, a12 equals 0, which means minus 3, 3, 3 minus 3 as the matrix and a11, a12 as the component as 0. And we solve it further, we get 3 minus 3 a11 plus 3 a12 equals to 0. This is my equation number 2. And we also get 3 a11 minus 3 a12 equals to 0. This is my equation number 3. Simple, very simple process, nothing complex about it. So we get the two equations. Now we have to solve a1 and a2. So for that to solve, we need the third condition that we have already discussed, and that is that if you go back, the property of orthonormality, which we have mentioned in the third. Okay, so this is what we are going to adopt. So what we are going to adopt is that as the orthogonality should be maintained, please make a note of this. A11 square plus A12 square should always be equal to 1. This is orthogonal transformation. Please make a note. Without this, you cannot move further or go ahead with the calculation. This is a condition which you need to follow again for generating the values of V or even U for that matter. Up to this point, any doubt? Okay. Now let's solve this. So if you solve this with the existing nature of it, so if you apply the second or third to on top of it, I'll just stop, leave out some steps over here. So you are getting A11 equals to A12. This is just by solving this two. Okay, we are just substituting on this from the equation 2 or 3 for that matter. You can take any one. So one of the expression is A11 equals to A12. And finally, we can get A11 as 1 by square root 2, which is equal to A12. I'm just dropping the calculation. The main calculation is there in the course manipulation. I am not doing that to save time. Alright. So we get the values of A11 and A12. Now, what is the significance of it? That is most important for you. So A11 and A12, we got it, right? So please make sure. So I'll just summarize. So sigma 1 for 8, we get A11 as 1 by square root 2 and A12 as 1 by square root 2. For sigma 2 equals to 2, in the same manner we are going to calculate, and we are supposed to get A11 for that as actually 1 by minus 1 by square root 2 and A12 as 1 by square root. So for both sigma 1 and sigma 2, we will calculate in the same manner and we will get two set of results. Now what exactly is meant by this? The first set of A11 and A12 forms the first column of the V matrix. So let me just write it down again. So you have the V matrix V. So you have the V1 column here and V2 column over here, right? So the entries of first A11 and A12. So first A1 is 1 by square root 2 and 1 by square root 2. And the next one is minus of 1 by square root 2 and 1 by square root 2. So basically, this is my V1 and this part is my V2. So from the eigenvectors, what we are achieving is the array for or the matrix formation for V. Again, no intuitive understanding. This is just from the calculated value. Okay, so these are my values of V. But what we need? We need V transpose. Okay, because in the equation we have V transpose. So we just take the transpose of it. So V transpose will be 1 by square root 2, 1 by square root 2, minus 1 by square root 2, 1 by square root 2. So you observe that we have already attained two of the decomposed matrix, sigma and V transpose T in the same order. Any doubt at this point? So let me just recap on what we did. We started off with the calculation of H transpose H. Alright, so we started off with this. We found out a matrix. From there, we tried to find out what are the eigenvalues. So we found out in this case, the eigenvalues are 8 and 2. Now for both eigenvalues, it can be interchangeable, but the only logic that we observe that these eigenvalues, as they are mapped to the singular value or the singular value array, we need to maintain that sigma 1 is to be greater than sigma 2. So naturally, my sigma 1, if I write it as square root of sigma delta 1, so this should be greater than the next one. So the orientation should be chosen in that order. Based on that, we found out what is my singular value decomposed at the first sigma matrix. Now, based on that, for each of the eigenvalues, we found out that what are the eigenvectors using A11 and A12. For each of the values, we got two values, and the interesting part of it, the impact is that for each of the column of the V matrix I'm talking about, that will be nothing but the first entries of A11 and A12 followed by the next entry of A11 and A12. Alright. So but in our equation, we require V transpose, so we take the V transpose. So what we are left with is to find U. Alright, so let's find the U part. So the U part is nothing but, if you see, let me write it down once again. So again, just to recap on the equation once again. So H equals U sigma V transpose. Everyone please follow this. So this is the equation that we have started off with, coming back. So what can be found out from U? So U can be 1 by sigma H multiplied by V. Okay, so we can just have a scenario of this nature when we are trying to find out what is my U vector. Alright, so it is basically for each and every column of U, you can find out 1 by sigma 1. So maybe I'll just write it down. For U1, it will be 1 by delta 1 H multiplied by V1. And for U2, 1 by sigma 2 H of V2. That will be my final observation. Now V1 and V2 we already know because we have already defined V1, V2 over here. This is my V1. This is my V2. So we substitute all together. So we get all the calculations done. So maybe I'll just not do that. So maybe I'll just write it down. 1 by square root 8. H is given by 2, 2, minus 1, minus 1, 1. V1 is given by 1 by square root 2 by 1 by square root 2. And if you do all this calculation, it will come as 1 and 0. Okay. This is the calculation. The final answer is this. So this is my U1. Similarly, your U2, if you calculate, it will be 1 by square root 2, 2, 2 minus 1, 1, minus 1 by square root 2, 1 by square root 2. And this, if you calculate, it will come as 0, 1. So my U, which is again a combination of the column, so U1, U2 is nothing but the first element 1, 0, 0, 1. So, but the problem here is not with the intuition. The thing is, this is a definitive solution that you will get. Otherwise, you have to search around that whether it is correct or not. Because see, the point over U is that each of the column, if you add up, it should come as 1. That is what's for the property. Now, if you say that this is 0, 1, 0, 0, 1, 1, 0. Suppose, you intuitively find out this. So 0, 1, 1, 0. In there also, some of the properties might be maintained, but in combination to sigma and V transpose, this is not correct. Understand? So that's why we are not opting for this and we will opt for this. So the final outcome, if I say in this way, so I know H is equal to U sigma V transpose. So we substitute the value of U, which is 1, 0, 0, 1. Sigma value is square root 8, 0, 0 square root 2. And V transpose is 1 by square root 2, 1 by square root 2. Minus 1 by square root 2 and 1 by square root. So these are my final decomposed output. And if you want to check them, that whether their properties are maintained or not, you will observe that they are maintained for sure. If you go ahead with the 6 properties that you already, one of the 2 properties we have already seen that it is maintaining. But even if after that, if you want to check all the properties like V transpose V is equal to V transpose should be an identity matrix. You just take the matrix, you multiply them and you will get the answer for it. My point over here is why we did all these questions, all these steps of this question is just to make sure that you have the understanding of how exactly SVD is performed. Now, given a chance, for example, I'll just give you a very simple example. You will find it a little confusing to get exactly what first of all, before going to this, is there any doubt in the process? Everyone clear with this? Okay. If I will tell you that if you want to confirm your marks on this, it's better to go ahead with this eigenvalue process. But if time doesn't permit you, intuitively you can do it, but you have a 50-50 chance that whether it is correct or not. It may be correct or may not be correct. Okay, that is the only thing. But if you follow this process, naturally the arrays that you are, or the matrix that you are forming, they will follow the property. That is what the thing is. Okay. So I will prefer you to do this, especially given the fact the steps and everything is provided with you, or it is there with you. Suppose I give you a question H is 5006. Find the SVD solution or a decompose using the intuitive method. Using the, it won't be mentioned, but I'm saying you, suppose that you have an H over here, can you define an intuitive way in forming three matrix U, V and U sigma and V transpose from this? Can you try at least? Try the SVD for the given question. Because if you follow the logic of the previous case, definitely you will come across UV and sigma for sure. But I'm saying just try out with the intuition, whether you get an intuitive approach to it. So one of the common thing, if you are doing an intuitive process, what I have found out when I was trying also in the same manner of doing it in intuitive way, is that make sure U and V, they are somehow an identity matrix ka form. Alright, so for example, I would try something like 1001 as my U, and maybe my V transpose also I'll follow 1001. Just intuitively. No logic behind it. Why I've chosen it. So I'll fix this two maybe, and I'll do the product multiplication. So whatever I'm getting as a resultant, I will try to fix that what can be the value of sigma or the capital sigma so that it fits the requirement. That can be one approach to it. Alright. Or you can change the position of zeros and one. I'm not saying that identity matrix you have to follow. You can also choose, someone might choose 0, 1, 1, 0, and this is my U, suppose, and your V or V transpose, he chose something like 0, like this maybe. In that case also you have to find out what should be your sigma, capital sigma, so that it follows because the final outcome should be this. So you can understand that is the problem with the general decomposition process, like intuitive method of finding the decomposition. Alright. So in this case, what I found out as one of the solution, I found out that if I follow U as 0, 1, 1, 0 and V transpose as 0, 1, 1, 0, my sigma should be around 6005. But as I said, this is only one of the solutions, because when you change the values of U and V matrix, your value of sigma will also change. So it varies. There can't be a single answer. But the most common thing and the most important thing is each of this matrix should follow the property assigned for that matrix. That is for sure. Okay? That is very, very crucial. Without that, even if the answer is correct, logically it is wrong, because the arrays or the matrix is not following the property. Okay? So there are some questions in here in the course material where I have tried to solve using different methods. I have tried giving all the properties one by one. Okay, solving all the properties in details. For example, the normal orthogonal property. Okay, suppose I give you a matrix, some matrix, then you have to prove orthogonality, the third principle. So basically what you have to do is column wise multiplication you have to do. Column wise, one column to other column, that's all. Suppose you have a matrix, I think I have an example. Just give me a minute, I'll just, for example, I'll give you, suppose I give you U equals to, this is just for your understanding, those who already know it, it's okay. But suppose I give you a U here. Suppose in some question, you have come across and you have found out that U is given by this. And you have to find out whether the columns are orthogonal in nature. So the easiest way to do it is, it's simple. Just column wise you multiply. Which means 1 multiplied by 0 plus 0 multiplied by 1, which happens to be 0. If it comes as 0, hence we can say it directly. This is a scalar multiplication, we usually do it. First column element multiplied by second column first element. First column, first, second column. That's all. If it comes as 0, we will say that it maintains the orthogonality. That's all. This one line you only have to do. That's all. Okay, so that's why when you are approaching this kind of question, it is better to use the eigenvalue process to get the final answer. If not, then try doing the intuitive process, which I don't think it is quite correct to do it, because there can be multiple trial and error, hit and run, and you may get a correct answer, you may not get a correct answer. But even if you get that, whatever the SVD, UV, W, UV, sigma you are getting, make sure that they follow the properties or not. That's all. Okay? So that's all from the SVD side. And the numericals, a few more numericals, as I said, it will be there in the course page, which I thought, I just thought of it because there is no such like direct question, I would say, which relates to WMC as such. As I said, SVD is a process which is adopted for matrix operation. So it is a general answers mostly, and most of the questions are related to matrix manipulation. That's all. So I tried giving some question in my course page. Please look at them, because the process that we have followed is followed for every question.
Once you are sure SVD structure.
Here, I will tell you that. I'll tell you that. Yeah, so that is how it is to be done. All right. So let us stop the process right now. So let me just give you some suggestions on catch-up.